All right. So it's a great pleasure to have Douglas Stanford from Stanford, who will give us a talk today about wormholes without averaging.
Okay, yeah, thanks very much for the opportunity to speak here. Let me just get my screen sharing going. Okay, so this talk is going to be based on a recent paper with these folks, Phil Saad, Steve Schenker, Shunyu Yao. And it's going to be fairly technical talk, but I hope also quite self-contained, because most of the time we're going to be talking about a very simple system. So, so I'll start with some kind of general introduction to the topic of space-time wormholes and averaging. So first of all, what is a space-time wormhole? It's a okay. So a space-time wormhole is a solution to Einstein's equations, or maybe an almost solution, but let's say for now just a solution to Einstein's equations that has a type of geometrical connection between different asymptotic regions, or between different very distant space-time points in a single asymptotic region. So for example, a picture that you might want to have in mind is something like this. We have some kind of wormhole like this, where the compact direction here, let's say, includes time. So that this would be the entire space-time geometry. For 1 + 1 dimensional space-time, we'd have a configuration like this, where there's some geometry connecting two asymptotic regions. Okay, and another possibility is you can have one that's connecting very distant points in the same asymptotic region. And I'll try to draw that like this. So we have, let's say, again, some 1 + 1 dimensional geometry. I've drawn the flat geometry here as bended over, so that we can draw, connecting them, a wormhole like this, connecting the two sides. So this is what a space-time wormhole is. It's a geometrical connection between either very distant points or between two completely different asymptotic regions. So these are interesting configurations to think about in general relativity, in gravity. And there's a long list of authors here of people who've had really important insights about these things. But the kind of question you might ask is whether they should be included. Like, should we include this type of configuration in the gravitational path integral? And okay, so the good news, the good thing is that in the last few years, including space-time wormholes in the gravitational path integral has shed some light on interesting non-perturbative aspects of black hole physics. So that includes this list of topics here: the eternal traversable wormhole, showing that black holes have random matrix statistics, deriving the Page curve for the entropy of Hawking radiation of an evaporating black hole, studying the late time behavior of correlation functions and statistics of operator matrix elements. It's like a lot of non-perturbative quantum physics, fine-grained quantum physics about black holes has been exposed or explained by using these space-time wormholes, including them in the gravitational path integral. So this is a good thing. We've been making progress. People have been making progress in understanding quantum black hole physics by including space-time wormholes in the path integral. Okay, so that's the good news. The bad news is that in at least some of these cases that I just discussed, and let me highlight which ones. So of these ones, it includes this case, and this case in the most direct way. So at least some of these cases, there's a problem or a puzzle called the factorization puzzle. And this was first discussed most sharply in a paper by Maldacena and Maus from 2007. So let me just tell you what this factorization puzzle is. So, so forget about space-time wormholes for a second, and let's just think about a very general question in a holographic theory. So where we have a boundary theory and a dual bulk theory. So here's the question. Suppose that Z here is some boundary partition function. Like maybe it's the thermal partition function of the boundary theory. And let's define a notation with capital B as a type of function that means evaluation in the dual gravity theory. So we have some partition function in the boundary theory, and we can consider evaluating it in the dual gravity theory. So for example, if that partition function is an S1 partition function, like a trace of e to the minus beta h, then evaluating it in the boundary theory might involve finding a two-dimensional surface that has that circle as its boundary, and then computing the gravity path integral on that surface. So the operation B of Z means compute, fill that boundary in with some bulk geometry. Okay, so now here's the puzzle. Suppose we take a product of two of these boundary partition functions. We'll write them as Z left and Z right. So let me draw them here. So we have these two circles. So here's Z left and Z right. Okay, and now we want to fill these in with some gravity computation. One thing we can do is we can fill it in with two copies of what we just discussed, two copies of this same disk-like geometry. But if we're including space-time wormholes, then we can also fill it in with something like this. And there are settings where this type of topology is a classical solution. And this, at least naively, is not going to be equal to B of Z left times B of Z right. Because B of Z left times B of Z right would just be the first line in this equation. So we have some additional contribution when we have a pair of boundaries. And that's obviously nonsense, right? Because Z left, Z right on the boundary theory is just a product of Z left times Z right. So if B is just evaluation of that in the bulk theory, then it should also factorize. And the wormhole is some contribution that is not factorizing. Okay, so you guys you probably heard about this before. If not, it kind of takes a minute to grasp, but it's a really fundamental puzzle about these space-time wormholes. Okay. So now let's continue with the narrative with some more, I guess, good news. So this is a good thing, which is the following. In some cases where these space-time wormholes have been discussed, the gravity theory where the wormholes exist, the bulk theory, is actually not dual to a specific quantum system. It's dual to an ensemble average of different boundary theories. So that's true in what's called the SYK model, Sachdev-Yekitaev model, and also in JT gravity, Jakiv tidal volume gravity. And in that kind of setting, non-factorization is okay. It's okay because you interpret B of some quantity Z as being an ensemble average of that quantity over some set of couplings that I'll call J. And as you know, if we have an ensemble average of things, so Z left, Z right, ensemble average, in general is not equal to Z left ensemble average, Z right ensemble average. So that fits. It fits with saying that the wormhole, this funny non-factorizing contribution here, the wormhole is just computing like the variance of this quantity Z in the ensemble. So that sounds fine. But now, okay, now this is finally the topic that we're going to discuss today. in this setting, we can ask, what happens if we just pick one theory from this ensemble? So in other words, what happens if we, let's say, freeze the couplings that we were averaging over in the previous step? Let's freeze those couplings, focus on one particular quantum system, one element of this ensemble. Then what happens to the wormholes? So if the wormholes are describing the variance of this quantity in some ensemble, then when we freeze to one element of the ensemble, there's no variance anymore. Things should factorize exactly. What happens to the wormholes? Are they still there? Or are they not? So in other words, we can make the factorization problem occur again by freezing the couplings. Okay, so that's the setting. That's the problem that we're going to discuss. By the way, I hope that you guys will ask questions during the talk. It helps me kind of stay on track, and so please do feel free to ask questions anytime you want.
Can I ask a naive question?
Yeah, please.
Yeah, so if this factorization puzzle exists, then it conflicts with which phenomena and that can be observed?
Sorry, if the factorization puzzle exists, does it?
Yeah, so I want to understand intuitively, then it contradicts with which phenomena physically?
Okay, yeah. Well, I don't know exactly what you mean by physically, but it's sort of it's just a contradiction. The factorization problem is just this contradiction. It's this contradiction here. It's the fact that b of z left right is not equal to b of z left times b of z right. And that means that b of z left, z right, and b of z left are not just evaluating those fixed quantities exactly. So z left, the partition function of the boundary theory should just be a number. And b of z left should just be evaluating that number in the bulk theory. And similarly, b of the product should just be evaluating the product of those numbers. So
didn't you just say that then you should not allow for these geometries in the path integral?
Right. So that's one perspective that you could take. And this was, I think, something that people were thinking about initially, just like don't include them. These are clearly causing a problem. They lead to non-factorization. Just don't include them. And if you had asked me a few years ago, I would have said, yeah, you just obviously shouldn't include them. I don't know why exactly. Something mysterious about the gravity integration contour or something, but definitely shouldn't include them. But look, when you do include these effects, they are giving you something good. They're explaining a lot of kind of deep quantum properties of the black holes. And so clearly there's something that is right about these wormholes. So I think it's too quick to just say that they should not be included.
So Douglas, if
Yeah.
you have just a single asymptotic region,
Yeah.
the analogous issue is failure of cluster decomposition?
Yeah, exactly. So just to, yeah, that's a good point. So let me just comment on it or draw a picture to go along with what Emil was saying. Suppose we have some very, very big region like this, and we can have a space-time wormhole that connects very, very distant points. And the way I drew it, it looks like the wormhole is long, but actually it can be a short wormhole connecting these very distant points. Then if you consider a correlation function of some operator here and some operator here, they might have very little correlation through this direction because they're very far apart, but they might be quite close together through the space-time wormhole. And since the space-time wormholes can connect points arbitrarily far apart from each other, that means that the correlator will not go to zero as we make the points very distant. So we'll have another type of contradiction with properties of the boundary theory, of the field theory.
Okay, thanks.
Okay.
Hey, Douglas.
Yeah.
Quick question. How are you defining exactly B of Z here? Is it just keeping all semi-classical saddles and maybe one loop determinants around them, or?
No. So B of Z in principle here means the exact computation in the bulk theory.
And full type 2B string theory with non-perturbative effects and everything included. Say we could do that?
Yeah, so assuming that you could do that, yeah. And these pictures here are supposed to represent some type of approximation to that. And,
isn't it that a full non-perturbative computation that does not know about the classical background you perturbate around? So you probably mean something more like all order in perturbation theory around each classical solution or something like that.
Well, no, I'm assuming something like the full non-perturbative computation in a semi-classical approximation reduces to something that looks like the configuration saddle points of the low energy theory plus additional contributions. And actually, we'll discuss kind of new types of contributions today, but the simplest expectation is that even in that full non-perturbative theory, if G Newton is very small, then it should be well approximated by a sum over semi-classical configurations of the low energy theory. And those, so the question is, do those include this and this, or just one? Right, so that's B.
Okay. Hi, Douglas. Can I ask you a question about the cluster decomposition argument?
Yes.
So these were bulk operators or boundary operators? I think this is a failure of bulk cluster decomposition, right? Is it clear?
Yes. Okay. Good point. If you want to make this argument precise, then we should make them boundary operators, and we can have very distant points in the boundary that can be connected by a short wormhole in the bulk. And then we can derive a contradiction with boundary cluster decomposition.
But can this happen?
Yeah, it can happen. Space-time wormholes can connect any point to any other point.
But at the boundary, you have both source and response, right? Both sources and operators. So it's not clear that.
Sorry, what's not clear?
For the bulk operators, I can understand, but for the boundary, it's clear because usually in holography you have two asymptotic behaviors near its point for the fields.
Well, but if we do have a configuration in the bulk where we have a wormhole connecting very distant points like this, then the correlation function on the boundary between those points will not be so small, just because those points actually aren't far away from each other.
Okay.
So in this case here, I'm just drawing a topology. I don't have a classical solution in mind, but this shows that if there were solutions like that, then they would violate cluster decomposition.
But I'm sorry, I thought that there was a theorem that says that any connection via the bulk of 2 points on the boundary has to be longer than on the boundary, right?
Well, this is a theorem about the space-time trajectories, which would apply to spatial wormholes. I'm not sure it excludes space-time wormholes like this. But it's possible that to get a configuration like this, to get into trouble with a configuration like this, we would have to study slightly off-shell configurations. As far as I know, there hasn't been a classical solution that people have discussed of this type that breaks cluster decomposition, but I'm just showing you that this kind of topology can do so. There are classical solutions that have been discussed for multiple asymptotic regions that break factorization, but it has a close analog for just one asymptotic region. There have been wormholes that have been discussed like this that kind of break cluster decomposition in time, but that's actually a good thing because cluster decomposition in time is not supposed to hold with finite entropy. So that's one of the good things that these wormholes do.
May I ask a question about the factorization?
Yeah.
I mean, the disorder situation, because you say that in the case of disorder, it's not a contradiction, but then you have to assume that the average is done not independently on the left and right.
not done independently. Right. So in this version, what you assume is somehow that the operation corresponding to B here, what that operation is it is the disorder average in the boundary theory. So there's no disorder in the bulk theory. The bulk theory itself is computing the disorder average of the boundary theory. So I'm not sure what you meant by averaging independently on the two sides. It's like the averaging only exists on one side, on the boundary theory. And that's dual to just a fixed bulk theory.
Right, but the boundary has two parts. And if each part has its own disorder and
Oh, yeah. See, sorry. I understand. You're asking about the second line. Yeah. It assumes that the couplings are the same on the two. So that the disorder average happens at the end. It happens at the time when you apply the B function, so that the two boundaries would have the same couplings.
Okay, but this is an assumption, right? I mean, it's not like you can.
Well, it's a thing that you can do. You can average at the end, and that sort of makes sense in this context of SYK and JT gravity, and that's the setting where you get a simple bulk theory that does contain these wormholes. So it's not really an assumption. It's just part of the definition of those theories, and yeah, that's how the correspondence to the bulk works in those cases.
Okay, thanks.
Okay, so let me continue. So this was just introduction on the topic of these wormholes and factorization. And what we're going to discuss is exactly this topic, but in a very, very simple setting. So we're going to work in an incredibly simple model. It's just going to be a finite dimensional integral. And I'll introduce the model in a second. But first, let me say what the results are. So in this model, what we're going to do is we're going to start out with a disorder average, and then we're going to freeze the couplings. And here's what happens. So first of all, wormholes persist. The wormholes remain even when you fix the couplings. That sounds like it's going to break factorization, so we have a mathematical contradiction. And the way that contradiction is avoided is that there are additional contributions that we call half wormholes that are present when you fix the couplings. And together, the wormholes plus the half wormholes lead to a factorized answer. So there's like an additional semi-classical contribution that you need to add, these half wormholes, which depend very strongly on the couplings, and which lead to factorization. And finally, multiple descriptions coexist. So you can think about, if you're computing z left times z right, you can either think about computing them together and including a wormhole plus half wormholes, or you can just do separate computations of z left and z right. So those are two different ways of computing this same quantity, and they give exactly the same answer if you do the computation precisely. Despite the fact that in one case you have a wormhole, and in the other case you don't have a wormhole. So it's quite non-trivial. Okay, so that's the executive summary. Now let me give you slightly more detail, and then we'll do it again in actual full detail with the equations. So the model that we're going to be discussing is basically, it's like an SYK-like model. It's an SYK model where we've replaced time by a single point, just to simplify things. So I should first explain, like, what is a wormhole in SYK? How will we tell that we have a wormhole, that we don't have a wormhole, that it survives or doesn't survive? What does it even mean to discuss a wormhole in the SYK? So I'm not sure to what extent you guys are familiar with the SYK model, but I'll explain precisely what model we're going to be computing in. So don't worry if you don't know what the SYK model is. But for now, just think of it as a quantum mechanical system, which we could imagine putting on a circle, computing the S1 partition function. So you could imagine computing z left times z right for the SYK model. And the way that the kind of bulk description of the SYK model works is that it's described in terms of these fields, G left left, G right right, G left right, that express correlation between the two different systems. So G left left expresses correlation between the left system and itself. G left right expresses correlation between the left and the right system. And a wormhole is just a configuration where G left right and its friend sigma left right, these two fields, are not equal to 0. So it's a configuration where you have non-trivial correlation in these collective fields between the left and the right. That's kind of what a wormhole does in gravity. It means that those boundaries are connected by a geometry, so there's correlation between them. You can have geodesics running between them. And in SYK, that just means that we have a collective field configuration where the collective field that represents correlation between the two boundaries is non-zero. Okay, so that's the definition of a wormhole in SYK. And here's the basic result of our analysis. Let's take this variable. So I'm going to discuss here sigma left right, one of these collective fields. And let me plot for you the action for that variable. Or let me plot for you, sorry, not the action, let me plot for you the sigma left right plane. So this is the complex plane of sigma left right. And so roughly speaking, what it looks like is the following. There are some points in this plane here where you have wormholes, wormhole solutions. So they have sigma left right non-zero, which agrees with our criterion from a second ago that non-zero left right collective fields means a wormhole. Okay, so we have these points where the that we call wormhole solutions. And when we study the theory with fixed couplings, this complex plane gets split into two regions. In the interior of some region, the action for those variables is non-self-averaging. Non-self-averaging. So what that means is that it depends very strongly on the particular choice of couplings that you make. The region outside this is self-averaging, which means that the action is basically the same in the disorder averaged theory and in the theory with fixed couplings. So you notice that the wormholes are in the self-averaging region. That means that they survive. That means that they don't care whether you fix the couplings or whether you're averaging over the couplings. They can't tell. The solution continues to exist. So mathematically, this is what it means that the wormholes survive in the theory with fixed couplings. But in the theory with fixed couplings, you have this region in the middle here, where the action is wildly, strongly dependent on the choice of couplings. If you average over the couplings, this region basically averages to 0. But if you fix them, then you have some large contribution, important contribution. And the largest contribution comes from basically the origin. And that's what we call this half wormhole contribution. So this is a picture of the integration space for this theory when you fix the couplings. There's a region where it remains basically the same as in the average region, and that's where the wormholes live. But then there's this new region which is strongly sensitive to the exact values of the couplings, and that's where these things called half wormholes live. So here's the kind of bulk picture to have in mind that goes along with this.
Sorry, Douglas, quick
yeah.
question.
Mm-hmm.
What can you say about the transition between the regions that are self-averaging and not self-averaging? Is there supposed to be a sharp line?
Yeah, there's a sharp line at large N.
I see. Thanks.
The origin of that transition is an interchange of dominance of two saddle points, and which is a sharp transition at large N. Okay, so this is the picture that you might want to have in mind for the bulk theory. So let's imagine that we're computing B of Z left, Z right. Then we can have the following contributions. We can have two disks like we drew before. We can have a wormhole. We can also have contributions where we have a disk and then half a wormhole. These half wormholes are the new thing. And the jagged red line is supposed to indicate that they have very strong dependence on the couplings. So you can have a disk and a half wormhole, you can have a half wormhole and disk, or you can have two half wormholes. Okay, and that the link, this red line linking them, is supposed to represent that these half wormholes exist in a theory where a wormhole was possible. Now, if you compute B of z left times B of z right, then you just get just the disk or the half wormhole squared. And if you expand this out, you're going to get 4 terms. You notice on the previous line, you have 5 terms. So it looks like there's a mismatch. And the agreement between the two computations is based on this identity here. What it says is that the half wormholes in the theory where a wormhole was possible, plus the wormhole, are numerically equal to the half wormholes in the theory where there was no wormhole to begin with, where no wormhole was possible. So you have 2 options of how to compute this quantity. You can do it in a way where a wormhole is possible, or you can do it where there's manifestly no wormhole and factorization is exact. And the 2 methods agree because of this non-trivial identity. Okay. All right. So that's the summary of our results. And the rest of the talk, I'm going to just explain in detail the model that we've been computing in and how we establish these results. I'm not going to talk too much about expectations for other systems. I just want to kind of focus on the model in the rest of the talk, but I'm happy to answer questions about that or answer any questions about this setup now before we get into the details.
I'm sorry, Douglas, just to make sure I understood. So your claim is that in this particular model, the product partition function is indeed the product of the 2 partition functions in the end.
Yes.
Okay, thank you.
Yeah, and it's true even though when you compute the product in one way, you include a wormhole. So previously, we discussed the possibility that you just don't include wormholes at all, right?
Mm-hmm, mm-hmm.
And here there's a way of doing the computation correctly where you do include the wormhole. You include the wormhole and you include some half wormholes. And they reproduce the answer that you would have got if you'd never included the wormhole at all.
But they have wormholes. Do they have a semi-classical meaning all the way?
Yeah, they have a semi-classical meaning. So what a semi-classical meaning means in this model is it means that it's a saddle point of the collective field action. Large N saddle point. And so my claim is that in the theory with fixed couplings, there's a saddle point here. This is a saddle point of that theory. And it's not a saddle point of the theory when you average over the couplings. It's a saddle point of the theory when you fix the couplings. So it's a new saddle point that appears when you fix the couplings. And its contribution depends very strongly on the couplings. And it averages to 0. Okay.
Sorry, do they have a semi-classical meaning on the gravity side?
Well, that's a good question, and we don't understand this very precisely in gravity, but our belief is that it looks something like the pictures that are drawn here. It looks like a configuration where you have a semi-classical geometry that looks like half of a wormhole, and perhaps it ends somehow in some kind of brane or some kind of boundary condition. That part we don't understand because our model is a little bit simpler than that. But that's one guess for what these half wormholes look like in gravity. It looks geometrically like half of a wormhole that kind of ends somehow deep in the bulk.
May I ask a question? Some very basic question. You speak about summing up some classical gravity configurations, but in fact, usually you have only one dominating. Yes, the other are exponentially suppressed.
Yes.
And why do you have this right? Or in rare cases they could have the same weight, but is it the case?
Yeah, exactly. Great. Yeah, that's the case. So the I claim in this picture you have two kinds of saddle points. There's these ones, and there's these ones, the wormhole and the half wormhole, and they have the same action.
This needs special tuning, or it's natural like that.
Yeah, it's because of something that I will explain. It can be explained by thinking about the disorder average of this quantity squared. The fact that there are, well, maybe I'll explain it now since you asked the question. It's a great question. Let me try to explain it. So far, we discussed the computation with, let's see, how can I make some space here? Okay, let me make a little space. So far, we've been discussing the computation with just two boundary theories. I'm going to represent them as points instead of circles just to save drawing. So we've been discussing something like B of Z left, Z right. And okay, and we can have a wormhole contribution which represents correlation between them. Now, what happens if we have four of these quantities and we compute the disorder average of four of them? Then we can have a wormhole connecting them like this, or we can have wormholes that connect them like this, or we can have wormholes that connect them like this. And there's a permutation invariance that means that these contributions are equal to each other. And the equality of those different contributions corresponds to the fact that the half wormhole and wormhole saddle points have the same magnitude. So there's a symmetry reason in the disorder averaged theory for why these contributions have the same magnitude. I don't know if that answers your question. But,
I don't know yet what is the model, but more or less. Mm-hmm.
Okay, yes. Maybe it will become clearer when we discuss the model.
Sorry, can I ask a question about the identity that you have down there?
Yeah.
Is there some sense in which the wormhole is like the diagonal part? Are you summing over the half wormholes? And yeah, is the wormhole like the diagonal piece of that, or?
Well, the simplest statement here is that the wormhole is the average piece. So if we take this identity, let's take this identity and let's average it over the couplings. Then it turns out that this averages to 0. And so you find that the wormhole, which is self-averaging, is equal to the average of the half wormholes in the theory with no wormhole. So it's right. Somehow the wormhole is capturing the averaging part of this complicated contribution, and
yeah, I see. It captures whatever doesn't vanish of the right-hand side once you average somehow.
Yeah, mm-hmm. And that sounds. I mean, one way to prove that without computing it is just to notice that the wormhole is self-averaging, and the half wormholes don't exist in the theory where you average. And those two facts imply that this must be true.
And is this a general statement? Because I thought there were cases where the wormhole is not self-averaging, like for the ramp, for example.
Ah, good. So that's because what we mean is a little different. So in the case of the ramp, yeah, what that statement means is it means that the wormhole is contributing to a quantity that is not self-averaging. So the ramp is not self-averaging. But there's a separate question which hadn't really been discussed before, but we're discussing now, which is, suppose we fix the couplings and study the contribution from the wormhole.
Yeah,
is that part of the answer, self-averaging?
Self-averaging. Yeah, that's a different question. I see.
Yeah, it's a more refined question.
Yeah.
So this, right. Somehow, both sides of this equation here are supposed to be not self-averaging. They depend strongly on the couplings. But there's just a part of it that you can isolate, the average part of it, and by definition, that's self-averaging. And in gravity, it's a little, sorry, in this model, it's a little non-trivial that it's self-averaging, but it can be shown to be true.
Thanks.
Okay, so let me, yeah, please.
sorry, one more quick thing, maybe.
Yeah, no problem.
So regarding the geometric interpretation of the half wormholes, if the defining feature of the wormhole was that it connects these regions, and the half wormhole doesn't, I'm struggling to understand how it's supposed to look different from some other solutions that cap off in the bulk, some soliton or something.
Okay, good. So in our model, let me tell you what distinguishes the wormholes in the model, the half wormholes in the model. What it is this. Suppose we're studying something. Let's call it just Z, not Z left, Z right. Let's just say we're just studying Z. Here's how you identify half wormholes. You double that quantity. You look at a wormhole contribution for the averaged theory when you double it. And then you just restrict attention to the left parts of that solution. And that's the configuration. So there's a precise sense in which that's half of a wormhole. It comes from the actual configuration of fields is the configuration that you would get for just a subset of the fields in a wormhole of a doubled quantity. So that's that's why we call it a half wormhole.
Thanks.
I don't know. Did that answer the question? I have no idea.
I feel I knew more than before, so
okay.
Yeah,
okay, sorry. Well, maybe, yeah. Okay. I feel like I've gone a little off the rails here. Let me try to get back on track. So let's actually talk about the model. So here's the model. What it is it's going to be the SYK model at a single point in time. So we're going to have n Grassmann numbers. So these are not Majorana fermion fields. These are just Grassmann numbers. And the partition function, z, is going to be dn psi of exponential of the following sum. So it looks a little bit like a Pfaffian, except that you have 4 fermions up in the exponential. This is an example of what people sometimes call a hyper-Pfaffian. And it depends on a tensor of couplings, J, A, B, C, D. So this is the quantity Z that we're going to study. It's an extremely concrete quantity. Draw some couplings, do this integral. That's what it is. So let's first study this in an average theory, and then we'll discuss the non-averaged theory. So if you average this quantity here over J, over the J quantity with an even distribution, you get 0. So the average of Z is 0. So it's not very interesting to consider the average of Z. But we can consider the average of Z squared. And we'll sometimes think of this as, label it as Z left, Z right. So we can consider this average. Okay. And let me write a formula for that average. If you just take 2 copies of this thing and average over J with a Gaussian distribution, you get something that looks like this. There's some number that we'll fix in a second. And then we have some ABCD, psi A left, psi, whoops, I'm going to run out of space here a little bit. So psi A up to psi D left times psi A up to psi D right. So that's the that's what you get after averaging over these J tensors. And you can rewrite this as some number times 1 over n, sum over A, psi A left, psi A right, to the 4th power. And it's convenient to pick the variance of the J couplings so that the number that goes here is just n over 4. So that's a choice of the size of the distribution of the fluctuations in the J tensor. Okay, so that's the disorder average of Z. And we're now going to introduce the trick. the trick that people use in studying the SYK model. It's like underlies the correspondence between SYK and a bulk theory. And here we're going to do see this trick in a very, very simple setting. So here's how we do it. We compute the previous line by doing the following. We include a new integration variable, g, and we insert a delta function that says that g has to be equal to this sum of these fermions. Okay, and then we just put g in the exponential. So we did nothing very interesting there. We just introduced a g variable with a delta function that says it's equal to this Grassmann bilinear. And then we replaced the Grassmann bilinear that used to be up here in the exponential. We replaced that by g, which is fine as long as we have this delta function. Okay, so that's step one. By the way, this g represents a left-right fermion bilinear. So I should write this as g left-right. It's the type of variable that expresses correlation between the two systems. So it's like the wormhole variable. If this is non-zero, it's like a wormhole. But to save space, I'm going to leave off the subscripts because we only have one g variable. So I'll just call it g. Okay. So, okay, second step in this trick is we write the delta function as an integral over some variable we call sigma. So in this step, all we did was we put an integral representation of the delta function. Sorry if this is a little bit too small to read, but we just put an integral representation of that delta function going from here to there. Okay, and now we can integrate out the fermions. So this is the final step in the standard SYK discussion. We integrate out the fermions. They enter only quadratically, and we find the following action. The integral over the fermions gives us this log of sigma term. Then we have minus g sigma, and then we have plus 1/4 g to the 4th. So now we have no fermions anymore, just an integral over these collective fields g and sigma that express the correlation between the two partition functions, between the z left and z right. So we've reduced it completely to an integral over these variables. And you notice that n multiplies the whole action. So if n is large, we can analyze this by saddle point. The saddle point equations say that 1 over sigma is equal to g, and that g cubed is equal to sigma. And these two equations together say that g and sigma should be 4th roots of unity. They should live on the unit circle, and they should be 4th roots of unity. And you find that the semi-classical expression for z, so we continue from here, is like 2 times e to the negative 3/4 n, just by plugging in these solutions and summing over those saddle points. So that's the semi-classical evaluation of this quantity. Okay, so I went through this in detail just to show you the trick where we introduce the g and sigma fields by first putting in this delta function here, then representing the delta function as an integral, then integrating out the fermions. And then we have a theory where we can do saddle points. Okay. Let me, okay. Well, okay. This is kind of a technical comment, so maybe I shouldn't have included it. But if you look at this integral here, sorry, it's getting a little messy, but if you look at this integral here, it looks like kind of an ill-defined integral. If you try to integrate that over g, it's going to just diverge. But it makes sense if you integrate over sigma first over the imaginary axis, so it's like a conditionally convergent integral. But you can rotate the contours and get a completely well-defined integral that looks like this. And this is well-defined integral for either order of integration. So this is just to show that this integral really makes complete mathematical sense. Okay. So the summary of this computation, we were computing the expectation value over these couplings of z left, z right. And we got a structure that looks kind of like this. Here's the left system, here's the right system. And we have a non-zero value, these non-zero saddle point values for the field that expresses correlation between them. So this is a wormhole. So this is kind of a distillation to this simple model of the concept of a wormhole in gravity. Okay, so that's kind of the starting point, that if you do average over the couplings, then you do have this wormhole that contributes. Now, if we had been computing z to the fourth instead of z squared, we can think about that as a pattern of correlation that looks like this. We have these three different patterns. We can have a saddle point where the left-right correlation and the left prime, right prime correlation is non-zero, or we can have two other patterns of saddle points. And there's a permutation invariance between the three of them. These look like the three Wick contractions you can have for Gaussian integral with the x to the fourth insertion. Okay. Okay, so now we come to the actual topic of interest in this model, which is the non-average theory. So we're going to do the same thing, but we're not going to average over the couplings. So let's just write out, start by writing out the quantity that we're trying to compute. So this is the quantity that we want to compute without any average over J this time. And we're just going to try doing the same naive tricks that we did before. So let's try to do this by integrating over some G variable over the real axis. And let's insert a delta function of G minus 1 over n, sum over A, psi A left, psi A right. So we just introduced the same delta function that we put before. And then we'll put this exponential n over 4, g to the fourth, minus 1 over n, sum over A, psi left A, psi right A. Okay, so you'll notice that, okay, so this is multiplied together. You'll notice that the second and third lines are just 1. If we integrate over g using that delta function, we just get 1. So this is a mathematically trivial, but mathematically allowable step. We have done something legal, although apparently not very interesting. Okay, so that was the first step. In the next step, what we do is we introduce a integral representation of that delta function using a sigma field, just like we did before.
Douglas, can I ask something?
Yeah, please.
So if the fermions were time dependent, like in the usual SYK, so this step is harder, or is it impossible to do? Or
No, it's possible. It's possible. Everything here makes sense in regular SYK. We think that it actually works the same way, but we can't prove it. So I'm discussing it in the simple model, both because it's probably easier to follow and because we can actually prove it. But the manipulations make sense in SYK, and I think that the conclusions would also hold in that case. It just isn't a mathematical fact.
So if I may ask, G is then a time function and sigma a time function? Is that what you would have in?
That's right. So you would have, in that case, you would have G as a function of T1 and T2. And you would set that equal to some fermion bilinear psi of T1, psi of T2. So you would have this type of equation instead. So you'd have more variables. The advantage of this model is that we just have one variable. So it's easy to discuss the integration contours and the entire complex plane for that variable. Okay. So you introduce sigma as an integral representation of this delta function, and then you rotate the contours like we did before. And let me just write the answer in the following way. We can write the answer like this. Psi of sigma times phi of sigma. Okay, so that's so far just some notation for the answer. Let's now explain what these functions are. But by the way, you should think of this as being like e to the minus the action for this collective field theory of sigma. Even now we've integrated out G2, so we just have one variable, and this is the action for that variable in the fixed coupling theory. Okay, so what are these quantities? So psi is integral dg of e to the n times minus I g sigma minus 1/4 g to the fourth. This is some concrete function. It's like sort of like a Gaussian, but it decays a little faster than a Gaussian in sigma. So it's a very concrete function. And that part is boring. The more interesting part is this part 5 sigma. And this is going to take me a second to write this down. Okay, it's that times psi a left, psi a right times sigma. And then we have minus n over 4 Okay, so this is the non-trivial part. So this is like, here's where the complexity of the fixed coupling theory is hiding. This very complicated function phi of sigma. It's a fermion integral that we don't know how to do explicitly. That depends on these couplings here. Depends on J, A, B, C, D. So one thing we can say about phi is what happens if we average phi of sigma over the couplings. Okay, that's not what we're trying to do right now, but let's just see what you get. If you do average over the couplings, then the average of this term here completely cancels this term here. And you end up with just a quadratic fermion integral. And in fact, you get sigma to the power 2n from doing the integral over those fermions. So the average of phi is some very simple thing. And if you plug that back in, you get our previous formula, the log term in the action for the previous computation. Okay. So now here's the key question about this model. How different are phi and the average? So the average over couplings of phi is some simple quantity, sigma to the 2n. We wanted to study the theory with fixed couplings, so we care about phi, not averaged. How different are they? Are these actually very different functions? And in what regions of the complex plane are they different? So the strategy to answer this is to compute.
Sorry, let me just warn you. I mean, there's been a lot of questions, so you can still you still have some time, but maybe 10, 15 minutes.
Okay, yeah, thanks. Yeah, I'm almost done. I'll just kind of, yeah, I'm almost done. So the strategy for answering how different they are is to compute the variance of phi, average of phi squared, and also the average of phi squared. And if these are similar to each other, then that means that the variable is almost self-averaging. So if these quantities are close to each other, then it means that phi of sigma is approximately equal to its average over couplings. So this is a way that we can answer this question. We can answer this question here by computing these two quantities in the averaged theory. So to answer it, we don't actually ever need to discuss the theory with fixed couplings. We can answer this completely in the average theory. And so here's what you do. You just compute this in the average theory, and that's not so bad. You can write an exact formula for phi of sigma squared, or you can do some saddle point evaluation. And in the interest of time, let me skip the details of that and just plot for you the answer. The answer is that the complex sigma plane looks like this, and this region is non-self-averaging, and this region is self-averaging. So phi squared is much bigger than average of phi squared in the interior of the blue curve, and they're about equal on the exterior. And the blue curve actually is a location of some interchange of saddle points in the theory for phi squared. So let me draw your attention to these points here. These are points on the unit circle. These are the fourth roots of unity, or a phase multiple of the fourth roots of unity that are the saddle points of the averaged theory. And you can see that they're well outside this scalloped curve. They're well outside, which means that they're quite accurately self-averaging. So that means that for these, as far as these wormholes are concerned, these wormhole solutions are concerned, the average theory of phi and the phi with fixed couplings are basically the same thing. And in particular, you'll have a saddle point at that location. But inside, it's not true. And the largest contribution comes from very close to the origin. The location close to the origin is this contribution we call a half wormhole. So, so let's see. So the key points here is that the wormholes persist. That is that they are in the self-averaging region. These half wormholes exist. That's the non-self-averaging region near the origin. And together they give a good approximation.
Sorry, Douglas. What you call a half wormhole, is it a saddle point or it's?
Yeah, it's a saddle point. It's a saddle point.
Okay.
It's a saddle point whose value depends strongly on the couplings, but its location does not. So you can picture a function that kind of always has a large maximum kind of near the origin, but the magnitude, the precise magnitude, and even the sign of that contribution can depend on the couplings. But the fact that you have a large contribution very close to the origin does not depend on that. Yeah, so it's a saddle point whose contribution depends strongly on the couplings. Okay, so well, maybe I have some summary page here of why we call them half wormholes. Should I? Maybe I'll say this just to explain why we call them half wormholes, and then I'll stop. So you can think of the contributions to z squared with fixed couplings. Think of those as the solid portions of this diagram here. So the left one corresponds to the wormhole. It's a correlation between the left system and the right system. And for now, don't worry about the dashed lines in the lower half of the diagram. And we'll just use this notation here to represent the sigma equals 0 contributions. It's sigma equals 0 because there's no correlation between left and right in these patterns. So these are the half wormholes on the right, and the thing on the left is the wormhole. And the connection between those and wormholes is the following. Now, suppose you take this formula for z squared and compute the average of the square of that. That is the average of z to the fourth. Now, that is given by these three kind of Wick contraction diagrams. The first one is just the square of the self-averaging wormhole contribution. And the second two, the second and the third, are the averages of the squares of these half wormhole contributions. So the contributions on the first line are kind of the underlying quantity that when you average it, square it and average it, you get a wormhole of the doubled theory. But for fixed couplings, they still exist, and their configuration is a half of the configuration of the wormhole of the doubled theory. Okay, so let me just stop at that point, and thank you for your attention and for all the nice questions.
All right. Thanks a lot, Douglas. Okay, questions for Douglas?
I have one more question. Is it clear that the notion of self-averaging or non-self-averaging is observably dependent?
I'm not sure exactly what you mean by that.
I mean that you judge whether an observable is self-averaging by computing the average or computing the observable without the average, and you compare them. But suppose I choose another object to do the same. Would I get the same region which is non-self-averaging?
Oh, let me try to answer. Let me try to give an example of that, and then try to answer the question. So you'll tell me if I'm answering the right question or not. So I claimed that phi of sigma was approximately self-averaging outside this circle. But you could imagine computing phi of sigma to the 100th power, some very high power. Maybe this is an example of a different observable like you were thinking of.
Right.
We could ask whether is this approximately equal to phi of sigma to the 100th power outside the blue circle.
Right.
Yeah, and so what happens is if you take a high enough power, it's no longer true. That in fact, if you take a sufficiently high power, like a power scaling with n, then it won't even be true at the locations of these wormholes.
Right. So you don't expect that. That's okay. But how about smaller powers or combinations of observables?
Yeah, for smaller powers, it's okay. And what this phenomenon represents is just that there are rare configurations of the couplings J where the self-averaging is not true. So the criterion that we discussed involving phi squared, that's enough to show that for most configurations of the couplings, it's approximately self-averaging. But the higher powers probe kind of rare configurations of the couplings, and there do exist rare configurations of the couplings where the self-averaging is not true, even near the wormholes.
Okay, fine. Thank you.
I had a question about non-Gaussianities in J, I guess. Can you go back down to your little plot? Yeah, so what happens if now you have a connected 4-point function for these dots?
Oh,
how would you think about that?
That would just, so suppose you have some configuration where you have some, okay, you have in mind something like, let me try to draw a picture now.
Yeah, exactly. Exactly.
Yeah, I think it would still be okay. It would just mean that you would have another kind of half wormhole that would look like this.
But this time it is correlated, right?
Yeah, so this time now the half wormhole configuration would not have sigma equals 0, but it would have sigma equals whatever it is here. So
yeah, I see.
So the configuration still makes sense. Actually, we have an example like that we studied in our paper. Yeah, so that makes sense.
Thanks.
Sorry, can I ask you a beautiful talk? What intuition does this give you for dimensions?
Well, I'm not sure it gives me too much. It gives me some, okay. What it suggests is that there is a way of computing things in the bulk theory of n equals 4 super Yang-Mills where you do include wormholes. You do include the wormholes, but you also have to include some other stuff. And the other stuff is presumably related to whatever microstructure makes up the microstates of the black hole. We don't understand it very well, but I think it suggests that there's a picture where you have both that and you have the wormhole. And there's also potentially a picture where you don't have the wormhole and you have a slightly different theory of the microstructure, and the two are equal. I think the most interesting question to try to pursue in that context, I'm not sure how to do it, but I think it's really interesting, is like, what are these half wormholes in the bulk dual of n equals 4? Like, assuming that the picture even somewhat makes sense there. Like, what is the analog of these half wormholes? We need these new semi-classical contributions that that compete with the wormhole and restore factorization. What are they?
If we take, let's say, what you described at face value, it would seem that one would have to consider some kind of wormhole, but cut with some particular boundary conditions, right?
Yeah, maybe it seems like perhaps that would be an effective description of the half wormholes. Some kind of effective description of the microscopic bulk theory of the half wormhole could be something like that, with a wormhole that ends in some kind of a boundary condition or a brane.
So just so I understand, so in n equals 4, is it true that there are two problems we could study? One, a black hole generated by a very heavy operator, right? We would put a very heavy operator and now we have a black hole, or put n equals 4 at finite temperature, right?
Mm-hmm.
These are two slightly different things, right?
Yes.
And what is the computation we should do in the first case, where I just consider n equals 4, I have a 2-point function, a very heavy operator, so I have a black hole. And now what is I think this is probably related to this clustering that you were mentioning in the beginning, but I could not follow exactly the technical.
You were asking how do we get some kind of a wormhole in that case, or?
Yeah. Yes.
Yeah. So let's take that state that you created with a very heavy operator, and then let's introduce two more operators, light operators. And let's consider the 2-point function at very large time separation of those two light operators. Then that will not go to 0 in the n equals 4 theory on the sphere. It will not go to 0 just because we have finite entropy. So we have some kind of random dependence on time. Mm-hmm. And I believe that its statistics, its late time, like the average behavior of that function, can be computed from a wormhole in the bulk theory, a wormhole that kind of connects early times and late times. And so to describe the specific function that you get in n equals 4 super Yang Mills, presumably you need to include the half wormhole contributions as well. But we don't know.
Yeah, that part I did not understand what you just said now. Can you explain it to the picture maybe?
Yeah, my iPad turned off. Let me turn it back on again. So, okay, so so what are we discussing? We're discussing some state where we have some heavy operator, then some light operator, e to the minus IHT, light operator, e to the IHT, heavy. So this is the correlation function we're considering. So in the boundary theory, I don't know, we have some kind of black hole that we formed. I don't know, we formed some black hole. And then we go to very late times in the boundary theory and compute phi, some 2-point function like that. And I believe that the late time behavior of this kind of function, its statistics, can be described by some kind of a wormhole. It connects these together. This hasn't been shown in that gravity theory, but I suspect it's true. And the claim extrapolating from these results in SYK.
Sorry, let me just understand first the intuition. So the intuition is that if I do it very naively without wormhole, things will just decay to 0. But I know that in n equals 4 they oscillate, so I need a new effect in the bulk.
Exactly.
That's why you want the black hole.
That's why the wormhole. Right. So exactly. So the naive gravity answer, I don't know, it's just this.
Right.
And the wormhole answer is something like this. It goes down, and then there's some other saddle point, and it goes up and does that. That's the wormhole answer. And now let's discuss the actual exact n equals 4 answer. Actual exact n equals 4 answer goes down, and then it like oscillates, probably something like this. So the claim is that, so clearly the wormhole answer is not right. The black curve and the red curve are not the same. But the claim, although this calculation has not been done, is that the black curve has the right statistics. And the even more wild extrapolation claim, but based on if something like my talk today works for n equals 4 for Mills, so on and so forth,
Sure.
then the claim would be that you are supposed to add this wormhole plus also a configuration where you have some kind of half wormhole. Something like that. And that together those things reproduce the crazy red curve.
I see.
And what would be the meaning in this case of going to this other picture, or this other picture does not make sense here?
The other picture, yeah, I think the other picture doesn't make sense if you just have a single boundary. I think you probably have to include this type of wormhole in that, no matter what. The other picture seems to make sense if you have, when you're talking about wormholes that connect different boundaries.
So can you explain again this curve, the black curve, the expectation? This is what people call the ramp. This is this ramp stuff. Is this thing?
Yeah. So there's a kind of ramp for 2-point functions as well as for the spectral form factor.
Is it easy to explain this curve, the black curve? Why does it go up and then stabilize? What's the intuition?
Yeah, the intuition is that, let's try to write this. Let's try to write this thing out as some kind of a sum over the energies, E and E prime. Well, let me discuss the case where we take a trace instead of the heavy operator. I think it should be the same, but I'm not 100% sure. So let me discuss the case for the trace, the thermal trace. So let's do trace e to the minus beta h of this stuff. Then if we write this out in the energy basis, we have something like this, E times phi, E phi E prime squared times something like e to the minus beta E plus E prime. So we have some expression like this. The one I wrote is actually not exactly correct for the correlation function that I wrote, but it's about right. You have a sum over energy levels of some kind of positive quantities, and then some oscillating piece. And the ramp is supposed to arise from a type of repulsive anti-correlation of energies. So that energies that are, they're kind of repelled from each other at long distances. It's not the level repulsion, it's a longer range effect known as spectral rigidity. And that explains this, that's the reason for this growth. But maybe that's a detail that isn't too essential here. The important thing is just that it doesn't go to 0. And if you look at the very late time,
what's this height? What's the order of this height? Is it exponentially small? Or?
Yeah, it's exponentially small because at late times, when you compute the average of this, you basically just take the diagonal terms in this sum.
Okay, now then I understand. Okay.
That's the thermal result, right?
Sorry?
Isn't that the thermal result?
Yeah, this plot here would be if we were computing it in the thermal state. I think it should be similar if we compute it in just a heavy, high energy excited state, but I haven't thought about that case carefully. But
okay, so these half wormholes, they don't have an interpretation in the boundary, right? They are something in the bulk. You need to add them in the bulk so that the usual boundary contribution has the usual properties that you want. I see.
Yes. Yes.
So it's not like we want to add some new to interpret some determinant operators or anything in n = 4 as this operators, right? It's not the case. Or maybe said differently, is there a way of subtracting some contribution from the n = 4 computation such that it would just remove these terms? Or
remove which terms? The half wormhole or the wormhole?
I mean, given that we don't know how to get either, maybe it's better to remove both, right?
Well,
First.
You can somehow average, well, you can kind of subtract the wormhole by like subtracting the part that you know to be there because of the statistics of these energy levels. Kind of do it by hand. I think your question somehow is, suppose somebody knew everything about n = 4 Super-Yang Mills. What would that person say? Oh, this quantity that I've discovered is your half wormhole. Like this number that I've computed here is the, and I think, like is it part of somehow like the CFT data of the?
Yeah, like if I cut this 2-point function by summing over all intermediate states, is it dominated by some particular intermediate state, right?
Oh.
In n = 4. That was what I thought.
No, I don't think so. I think it receives contributions from a whole bunch of states.
Then it will not have a natural interpretation in n = 4, just in the bulk.
Probably not. I think it's probably not related to a state in the bulk. It's related to a state in the boundary. It's not a state in the bulk either. It's like some. Okay, there's an analogy. Okay, let me ask and try to answer a relative of your question. Let's forget about n = 4 Super-Yang Mills for a second because it's complicated. Let's think about a simpler chaotic system, just like a particle bouncing around in some billiards system. Then the analog of the CFT data of n = 4 Super-Yang Mills would be like computing all the energy levels of that particle in this irregular shaped stadium. Like you just have a list of all the energy levels. And you could ask, is there an analog of these half wormholes? Do they correspond to like one of those energy levels? Like what is going on there? And so Steve Schenker, Phil Sod, and Shunyu Yao are writing a paper about this. And roughly what they say is that the half wormholes correspond to not energy levels of the particle, but they correspond to an aspect of the sum over periodic orbits. So it's like, from the boundary perspective, it's like a dual picture. You have energy levels or you have the sum over periodic orbits. And the half wormholes correspond to some property of the sum over periodic orbits, not directly to the energy levels. So I don't know what the analog of the sum over periodic orbits would be for n = 4 Super-Yang Mills.
May I ask a wild question?
Yeah.
Do you know that for instantons where the theta vacua were invented to restore cluster decomposition, people have been using merons. They are half instantons, and I was just wondering whether that could be useful or not.
I don't know.
This was 40 years ago, so I'm not quite sure.
Okay, I don't know what a meron is. Can you explain it? Or
no, it seems still to exist in the literature, but barely.
You can think of it as
a half zero size instanton.
With half topological charge, whatever that means.
Half in what? Okay.
But they are not self-dual solutions, so yeah, it's just a wild guess. Sorry.
In fact, there are wormhole solutions with merons, supported by merons. And I don't know if Elias has also half wormholes in some old paper with Kostas Bachas, but I'm not sure.
Good.
I'm not sure if they can be half wormholes, but we'll think about it.
Okay. Yeah, thanks for the comment. Sorry, I can't say anything at all useful.
Thank you for your talk.
So, when you draw a half wormhole, you draw some squiggly line.
Yeah.
Is that supposed to be a particular fixed boundary condition of some sort? Are there an ensemble of half wormholes, or is this a half wormhole?
Okay. I think I understand what you're asking. So let me try to answer. So when we say half wormhole, what we mean is we're talking about configurations of these collective fields. So you should think about it as like we're talking about configurations of maybe the metric kind of far away from this boundary condition. And whether there's a boundary condition or a sum over boundary conditions or a sum over microstates or something there, maybe it doesn't matter too much for the perspective of the metric outside that region. And so what you describe as just kind of one configuration of the metric might fundamentally be a sum over a whole bunch of different things that can be going on at that cutting surface. But the metric might not know about that.
But the way you're describing it now, they look a little bit like fuzzballs, right?
Yeah, maybe the fuzzball is the sum over fuzzballs is like the fundamental. Yes, it's something like that sounds very interesting.
Yeah, that's why I was wondering, is it a saddle or is it an ensemble of saddles or?
Well, but suppose we study fuzzballs and we just ignore what's happening closer than some distance to the horizon. Then maybe we would say that they're all the same.
And you replace them by a black hole, right?
Yeah, you replace them by a black hole, or good. Or maybe there's a fuzzball theory of wormholes too, that sometimes
that would be probably the analog. But if we go back to fuzzballs, in that case, what we think is that a single fuzzball is one of the possible states of a black hole. But as far as the area around outside the horizon is concerned, you just replace it by a black hole. You forget which fuzzball it was, right? And that's what you do. Now, if we go to your example, the question is, of course, your at least if I understood correctly the way you described your half wormhole, it is for a specific set of couplings, not all possible couplings, but a specific set of couplings. It looks like the analog of a microstate of a black hole, like a fuzzball. But at least for some things, you could replace it by something that doesn't depend on which particular couplings it depends. But that clashes with your claim that the particular saddle depends strongly on the type of couplings.
That might be because you're discussing a case where the fuzzball is kind of, the fuzzball idea is applied to the black hole solution, like the thermodynamics of the black hole solution, which is self-averaging. Maybe there's a similar thing that you can do where you study fuzzballs or something like fuzzballs in the context of a wormhole, which contributes to something non-self-averaging. So maybe there's a different set of fuzzballs that we have to sum over somehow in order to.
But are these wormholes?
Are they what? Sorry.
Are these wormholes?
Which
are these? They are decoupled geometries or they are connected geometries?
Well, the vague picture I was thinking about, and I thought that you were also thinking about, is something where you would have decoupled geometries that would be fuzzball things that would somehow mock up the wormhole.
Right, but in that case, you need somehow to end the geometry somewhere, right? And then you're getting back to the original question. How do you end it?
Well, maybe the fuzzball takes care of how it ends. I don't know. I think it's obvious that I'm speculating wildly beyond any kind of reasonable basis.
So to bring it back to a concrete question. So I think maybe one of the things that's confusing me was not understanding a picture you drew earlier in the talk, where you had contributions from disconnected geometries, and then there was one of your 5 things, which was 2 of these half wormholes connected by a red line.
Yeah.
What was the red line?
Good. The red line was I deleted that diagram, unfortunately. Okay, I deleted it to make space for something else. The red line was saying that those half wormholes were existing in a theory where you had introduced the the wormhole field. So let me try to explain that mathematically. Oh dear. Forget about this text, but just look at this equation here.
That thing down at the bottom left, what is that?
Well, I'm getting there. I'm getting there. I'm getting there. Look at this equation that I just selected here. I don't know if you can see it, this equation. So this is the equation that introduces the wormhole. So G left right is kind of the wormhole field. It's the wormhole variable. Now, after we introduce this variable, G left right, we study saddle points of the theory for G left right and sigma left right. And these pictures here correspond to saddle points. Sorry, the pictures on the left correspond to saddle points of that theory. So this is when G is equal to 0. And this is when G left right, whoops, is not 0. So, right. That's what those things on the left are. What's the thing on the right? This is the theory with no G left right. This is where you didn't introduce this G left right variable and its accompanying delta function at all. So there's
So you mean the original formulation of the theory in terms of the fermions?
In terms of the fermions, or not necessarily in terms of the fermions, just in terms of collective fields of just the left system and the right system.
Oh, I see.
But you just don't include this. You don't include this step at all.
So the right-hand side of this picture, that could be the basis of possible configurations in sort of a double theory. And then you could use the left-hand side, or it is the point that you can use the wormhole configurations if you are interested in sort of some average quantities, because doing the computation with the configurations on the right is too difficult.
Yeah, okay, good. So you're asking why would I ever use the left side instead of the right side?
Well, that's one question. And the other question is, so if the right-hand side describes the full sort of microscopic configuration where you have all the details in half of these geometries or solutions that may not be geometric, then you should not include both the wormhole and the right side configurations, right? Because then you would overcount.
Yes.
Like the left side is, so the wormhole on the left would be the approximation, a good approximation to the right-hand side in an average theory.
Yes.
Where the half wormhole doesn't contribute. And maybe the half wormhole is a good approximation to some other question where the wormhole doesn't contribute, I don't know. But if you wouldn't include both the right-hand side and either of the two on the left-hand side together, because that would overcount.
That's right. Yeah.
So if we say that for example, the wormholes explain something about the page curve, you could, if you had the computational power, you could do the computation just using the configuration on the right-hand side, but then you wouldn't also include the wormhole configuration on the left, because that would not give you the right answer.
Yes, yes, that's right. Mm-hmm. Somehow the difference, since you mentioned the page curve, an important feature for the case of the page curve is that this piece is much bigger than that piece. So kind of for the page curve, it's like a good idea to just do the wormhole, a good approximation. Never talk about half wormholes.
But when you say it's much bigger, like what's the correction? What's the mistake that you make? Is it that you don't go exactly to 0, or?
No, it's just that for the page curve is computing a self-averaging quantity. So that the way that happens is that the half wormhole contributions are really small in that case. So earlier we discussed that the half wormhole contribution and the wormhole are like basically the same order of magnitude. And that's true for quantities that are supposed to factorize. But for quantities that are not supposed to factorize, like the entropy quantities in the page curve, it's no longer true. And in fact, the wormhole contribution should be much, much bigger than the half wormhole contribution. So that's a case where like the left-hand side is clearly a very efficient tool, because to a very good approximation, you just ignore the half wormholes and just compute the wormhole. But for these quantities that are supposed to factorize, the left-hand side is not so efficient because the two quantities are of the same order. like what it would correspond to in this plane, the sigma plane, is that we would still have the same structure, something like this, I don't know. But the contribution near the origin would be much smaller than the saddle points outside. And whether that's true or not depends on the type of quantity you're computing.
And how many types of those half wormholes exist for a given, well, like this is the set of all these saddle points that have, well, there's a collective field, and it depends on how many such configurations there are, how many saddle points there are, depends on what fields you have, how many fields you have.
It depends on how many saddle points you have, wormhole saddle points you have when you double this configuration. So for this case, we would double it, which means we would consider 4 of these boundaries, and then we can have wormholes like this. And if I cut it along here and take the top half, I get this thing. But you can imagine other configurations, as we were discussing earlier. You can imagine these kinds of configurations. And now when I cut it, I get something else, and I would have to add that now. Now I have to take this equation, and on the left-hand side, I would have to add to it this, I have to add this thing. So to kind of figure out what set of half wormholes you have to include, you just double it and look for ordinary wormholes. Well, that's how it works in this model. And I don't know how it works in gravity or if it works at all.
Maybe another question. So a lot of times people have made the criticism that, okay, you have all these possible solutions, but you should also include all the other saddle points. So in addition, you should include the wormhole. From this equality that you're right, it doesn't seem right that you should include both, but is there another argument why, like what before this, what one would one have said that one should not include both wormhole and possible configurations at the same time in the computation? From this equality, it seems like because you would overcount if you include both, that you shouldn't do that.
Well, but what about the left-hand side? There you're including both the wormhole and these half wormholes.
Mm-hmm.
And it's not overcounting. So whether it's overcounting or not here seems to depend kind of on whether you're considering the half wormholes in the theory with the G left right variable or without the G left right variable. And if you're considering the half wormholes in the theory with the G left right variable, then you had better add the wormhole too, and it isn't overcounting.
Mm-hmm. Douglas, can I ask a question here? If you have a single asymptotic boundary, can you make a similar process, including, I don't know, microscopic wormholes with a single asymptotic boundary plus semi-wormholes? Because then it would be more clear what you're adding and subtracting, right?
So you're asking whether something like this equation could apply for a single boundary, and I guess so.
And then, yes.
I guess so. Yes, yeah, I think so. I wasn't sure where you wanted to go with that.
Well, there it might be easier to understand what these configurations would be, or what needs to be done, or I don't know.
Mm-hmm.
Because now we have two problems, somehow it's a bit harder to.
You mean two problems, meaning one boundary or two boundaries?
Yeah, exactly. We have both two asymptotic regions and adding two types of states. While the other we have a single asymptotic region, we say we have n equals 4, and we try to add the two types of.
Yeah, somehow in the case where you just have one boundary, in that case, I'm not sure we should expect to have the right-hand side here. I think in that case, maybe we only have the left-hand side.
Yes.
Because I don't know, if you only have one boundary, I'm not sure. I don't know. Do you think it makes sense to restrict to just like topologically trivial configurations or something? Maybe, but that sounds funny. Yeah, I don't know.
May I ask a question?
Yeah.
What about the bad news which you announced at the very beginning? Now you can check what's going on because in principle you know what is the boundary theory, yes, in SYK model. So what happens to these separated boundary theories? How the paradox can be resolved?
So the claim is that it can be resolved by saying that this is not complete. You need to add also half wormholes.
Mm-hmm. But how does the boundary theory feel it? What will happen to it? I mean, on the boundary, you usually have something like Schwarzian action. What will be the difference for this bulk, for the bulk boundary correspondence?
Okay, so I think of the Schwarzian action as part of the bulk theory, not the boundary theory. It's like a boundary mode in the bulk theory. And from the perspective of that theory, of the JT gravity theory that includes the Schwarzian, you would just have to add some new saddle points.
Is it clear what are these in the language of this version? The half saddle points, the half wormholes?
Well, no, it's kind of clear what the configuration should look like near the boundary, but it doesn't clear what happened in the bulk. Near the boundary, it should look like part of this trumpet configuration in the Schwarzian theory and the kind of trumpet geometry. And then it isn't clear what happens deeper into the bulk. Yeah, so unfortunately, I can't say more about that. It would obviously be nice to have a better understanding of what this would look like in the bulk theory, in the gravity theory.
Yeah, I think we should give Douglas a break. In any case, I think it's time to stop the recording. So